Hi, I'm Alex Tong, and today I'll be talking about our project of interpolating Wasserstein Barycenters on patient manifolds. So today I'm going to set up the problem and give it a little background on Wasserstein Barycenters, and I'm going to show how this can be used in the time series samples and how it can be applied to more general sets of samples. Recently, there are a number of measurements that give features at the single cell level. This can give insight into many aspects of development and disease with great precision, especially when there are heterogeneous effects at the cellular level. However, this type of measurement is expensive, in part because these features measure features over a set of cells per patient. Here, we view single cell features as samples from a distribution of cells of each patient. The problem we are concerned with is how to infer a single cell distribution for a patient based on a library of existing single cell measurements. This can be abstracted to a problem of imputing distributions given a set of outside features. We will first take a look at a simplified problem of imputing along time. Here we have a series of measurements where each measurement is a distribution, and we would like to interpolate between successive measurements. You can see on the left a scatter plot of these cells and how the distribution of cells changes over time. We have samples at discrete time points and would like to interpolate continuous times. So two pieces of related work you should be aware of. In Waddington-OT, the authors calculated the probable ancestors in descendant cells using optimal transport, and they evaluated the effectiveness of the fit with parallelized barycenters in one dimension along time. So VMD used Wasserstein distances between single cell distributions, but did not interpolate. So here we extend the interpolation to the multidimensional case study in VMD. So next we will formalize our notion of means, or Barycenters, as they're called in the optimal transport literature. For some weights in this distance function, we can look for the point that minimizes the weighted distance to each of our reference points. Depending on the distance chosen, we'll get different mean points. When we generalize this to distributions, we have more options of how to optimize this mean. A Wasserstein barycenter minimizes the Wasserstein distance to the reference distributions instead of using the more standard L1 or L2, also known as Euclidean distances in the single point case. The general optimization is very difficult. So in previous work, the space is often discretized into a grid, and we optimize the weights over the grid. And here the size of the point represents the relative weight in the final barycenter. Another example in 2D from Curie and Doquette, we have a data set of concentric ovals. So in this case, the Euclidean barycenter has a very different form than the Wasserstein barycenter. So in some circumstances, one may be preferred over the other. In general, there are three parameters of high significance when considering barycenters over distributions, especially in high dimensions. The distance between distributions used, Wasserstein versus Euclidean, the ground distance if the Wasserstein distance is chosen, and the domain to optimize the barycenter over, as we saw in the previous example where we chose a grid. In general, for t equals 2, I mean between two distributions, this is solvable through the mechanical interpolate, as done in Waddington-OT, which we do not have time to go into detail here. For more than two distributions, then we need to constrain the domain of x of the distributions that we optimize over. Typical choice is to use the support of the reference distributions and learn new weights of these discrete points, or choose a grid. However, this doesn't work in high dimensions. We'll next show when this might be a good or bad choice. So a single cell is often thought of having a smooth, low-dimensional support in high dimensions, which has manifold-like properties. Here we look at a distribution moving along one dimension, embedded in two dimensions. We are given distributions at time 0 and time 1 and want to impute the distribution at time 1/2. This example where we might want to use the barycenter on a restricted support because the other ones go off the manifold or do not reflect the support well. So here we restrict the support to the input space and compute the barycenter. The loss is the closest to the target distribution. Next, we look at a real single cell data set of 300,000 cells over 42 time points. We would like to impute this one-dimensional manifold. The task is, given distributions at t I-1 and time I+1, we impute the distribution of cells at time I. Then we evaluate the difference between the interpolated distribution and the ground truth for different methods. So this is showing different methods. Here we measure the mean EMD over all 41 interpolated time points for different choices of parameters. Here we find the mechanical interpolate performs the best with geodesic distance, but this cannot apply to more general settings with more than two distributions. We find the geodesic distance with extra support points that are randomly imputed from the other samples works best. We adopt this strategy for imputing on more general higher dimensional manifolds. So this is a more general higher dimensional manifold. So we have a faceted set of COVID functions, 200 patients, 53 healthy, and 156 with COVID. There are monocytes on a low dimensional fate projection. We show the distribution of cells, of all the cells in gray, and picking out a set of example patients, each in red. We take the Barycenter between all 53 healthy samples to get a baseline and compare this baseline to the background to find differences in cell counts and distribution between healthy and sick. The second way we can apply Barycenters is to impute between different disease states. So imputing between moderate and severe or healthy and moderate, we can get a more continuous picture of the disease progression. And so here we show how we interpolate on the graph and then compute samples from this. So in conclusion, Barycenters are a very fancy term for weighted averages of distributions, but there are many choices, and they must be computed on some predefined support for higher dimensional and more distributions than 2. For single cell, the obvious choice is to use the background measured cells or random interpolations. We find these modifications provide better interpolations against ground truth. Thanks for watching. Please let me know if you have any questions at the email above.